Hey! Welcome to Tech News Station. Today we'll talk about star as seen dragging space-time with it. So let's begin. Scientists studying tiny changes in a pulsar's signal have proven that massive rotating objects drag surrounding space-time around with them as they spin. The process, called frame dragging, was predicted more than a century ago by Austrian mathematicians Josef Lense and Hans Thirring, as a consequence of Einstein's theory of general relativity. But that doesn't make it easy to measure. It is a very subtle effect, says Ramesh Bhat, an astrophysicist at Curtin University in Western Australia. Prior efforts to measure it had been conducted via satellite experiments in the gravitational field of the rotating Earth. But the Earth simply isn't massive or rapidly rotating enough to make the best laboratory. Instead, Bhat and colleagues from Australia, Germany, Denmark and New Zealand turned to an unusual astronomical pulsar known as PSRJ 11416545, which researchers have been studying for 20 years via Australia's 64-metre Parkes radio telescope. Pulsars are tiny, hyperdense stellar remnants that emit very, very regular radio signals. Pulsars are cosmic clocks, says Vivek Venkatraman Krishnan, from the Max Planck Institute for Radio Astronomy, Germany, the corresponding author of a paper in the journal Science. PSRJ 11416545 is no ordinary pulsar, however. It's a pulsar in orbit around an extremely rapidly rotating white dwarf star, itself only the size of the Earth, but 300,000 times denser. That's not as dense or small as the pulsar itself, which is probably only 20 kilometers across and 100 billion times the density of the Earth, but still, these is an extremely unusual pair of astronomical objects. Before moving forward, subscribe Tech News Station and press bell icon. Better yet, the white dwarf is rotating once every 3 to 4 minutes, while the pulsar is circling it about once every 5 hours. All of which, Bhat says, means that the frame dragging effect at PSRJ 11416545 is 100 million times stronger than in Earth orbit. To measure it, the team studied the arrival times of PSRJ 1141-6545's pulsar signals for 20 years. What they found was a slow change, in the order of 1.5 parts in 3.5 million, indicating that the pulsar's orbit was slowly changing orientation in response to the frame dragging effect of the nearby white dwarf. It essentially changes the orientation of the pulsar's orbital track, but by an extremely tiny bit. Bhat says, adding that this was why it took 20 years of patient monitoring to spot it. But the result, he says, was worth the effort. This is yet another stunning verification of Einstein's theory of gravity, which is undeniable, shining even a century after its formulation, he says. No other theories have been explored or proven to that depth and rigor. Einstein's theory is most definitely the theory of gravity we should continue to adopt. It is also the foundation theory we use to understand how the universe works, how it has come about, and how it evolves. And how best to describe this concept of frame dragging? If you are after a useful analog, visualize a spinning ball in a bowl of thick syrup. Here the ball is like white dwarf and syrup is like the fabric of space-time, Bhat suggests. Thanks for watching video. Hope to see you guys again. Goodbye.